Okay, so in this video we're going to do a proof of the parallel axis theorem, and when we start this proof we're basically going to use kinetic energy to establish the fundamental and the underlying principles behind the proof. This does have an important application or implication whenever we get into doing conservation of energy problems, so I think it's really good that you see the proof for the parallel axis theorem, because it really does give us insight into how to set up conservation problems later. So to do this, we're basically going to start with an underlying principle here of what's going on, and that is that the total rotational kinetic energy of the object, this is the total now, it's going to be equal to the kinetic energy due to the motion of the center of mass, because remember that the center of mass represents the entire object, and so we don't really care about direction as long as there's a speed associated with the center of mass. Then the object will have translational kinetic energy. So it's going to be the kinetic energy of the center of mass plus the kinetic energy of rotation. So this is going to be our foundation for the proof. Okay, so now that we have the foundation to our problem, let's just take a look at some of the reasoning behind it. So our center of mass is going to be located right here, and we're also initially going to place the axis of rotation at that location, so that if you were to spin the object and cause it to rotate, so omega is going to be in that direction, then what's going to happen is the center of mass is not in motion, and so the total rotational kinetic energy is just going to be equal to our definition that we use for rotational kinetic energy, which is 1/2 I omega squared. So we can fill in part of this equation. So remember that this K rotational, it's entirely due to rotational kinetic energy when your axis of rotation is through the center of mass. So we can write this as 1/2 I, and I'm going to put ICM so that we have that reminder that it's the moment of inertia for when the axis of rotation is through the center of mass. So this is generic. It's not specific to using the rod here. This can be for any geometry. So it's going to be 1/2 I omega squared. Okay, now where things change a bit is whenever we move our axis of rotation. And just for simplicity, if we move it all the way to the end down here, then we're going to move it through that distance d that we saw in the previous video. So it moves through that distance d, and now what ends up happening when this rod is rotated, so in this counterclockwise direction, the way I've drawn it, the center of mass here is also going to be rotating with the same omega as the end of the rod. Okay, all points will have the same angular velocity, but not all points will have speed. Now remember that the translational kinetic energy is associated with motion of the center of mass. And since the center of mass is no longer fixed in space, we now have a 1/2 mv squared. And remember, that's just for the center of mass. And then, of course, K rotational for the whole object now becomes 1/2 I omega squared. And this I is the new moment of inertia for the entire rod. Okay, so we're almost done here. We're not quite finished. What we have to do now is we have to cancel some stuff out and make a couple of changes here. So first, let's do some canceling. All these 1/2s go away. And we need to convert velocity, because it's translational and not rotational. We need to convert this velocity into angular velocity. And we do that using the bridge equation, v is equal to omega times r. Now, in this case, omega is, well, that's going to be the same, right? Omega is always going to be the same. But r, in this case, is going to be the distance d. So we can write v is equal to omega d, and that's going to give us I omega squared is equal to m omega squared d squared plus ICM omega squared. All right, and now we can see that the omega squareds are going to cancel with each other. And we're left with I is equal to md squared plus I through the center of mass. And that's it, we're done. This is the parallel axis theorem. We just have to rearrange it into the standard form, you know, move these two terms, switch them with each other, and we get I is equal to I through the center of mass plus md squared. Now is the appropriate time to at least mention it so that you can connect the parallel axis theorem with what I'm going to do in a later video associated with conservation of energy. And basically, what happens with conservation of energy is that we oftentimes, in physics in general, if you're not careful, you can fall into a rut just out of habit, writing certain things because you've seen them often, and you know, you can't seem to figure out why you can't maybe get a new problem to work. I'm going to go through some examples of that, but here's the point. When you set up a conservation problem, it's very common to use for kinetic energy 1/2 I omega squared for I through the center of mass of the object. So for example, if you have a ball which is rolling down a hill, we would typically use the axis of rotation as the center of the ball, which is rolling down the hill. And that makes sense because clearly there's a rotation there. And in this scenario, for doing conservation, you would say that all of the gravitational potential energy is going to be equal to because the ball is moving, we would say it's equal to the translational kinetic energy plus the rotational kinetic energy of the ball. All right, but it's set up like this only because K rotational is based on I through the center of mass. But what happens if you pick the point of contact as your axis of rotation? In that case, what we would get is UG is equal to K rotational, and that's it. There is no translational component to the problem. And the reason for that is this K rotational is 1/2 I omega squared, but this I is no longer I through the center of mass. This is going to be the I that you get here, and this I already includes what's going on with the center of mass. And so we no longer need to worry about writing K translational. And so I'm going to give more details about how to do this and to be able to switch back and forth between these two particular strategies. All right, so this is the parallel axis theorem. The proof itself is pretty straightforward. just make sure you study the notes, that we have here for what these individual terms mean. You want to make sure that you're not stuck in that rut of, oh, okay, I recognize the algebra without conceptualizing the algebra, because this is one of those cases where it's really important that you conceptualize the algebra, because what I'm going to do in the next video, or when we do conservation of energy with rotation, is I'm going to point out that, very specifically, I have not seen what I'm talking about up here, this stuff. I have not seen this addressed explicitly in a textbook. It's almost as though it's assumed. So we'll look at that then.